Hello, everyone. Uh, Welcome to Champ. You'll know the rules, and so we'll just go ahead and get started. I am extremely pleased to introduce Janet Page, who's going to tell us about extremal singularities in positive characteristic. Janet.
Great. First of all, thank you so much to Carrie and Elisa. Also for your patience in coming back after I had so many technical difficulties last time. But anyway, it's an honor to be here talking to you all. And I'm so glad that you are all able to be patient with me and come back a second time. All right, so I'm going to be talking about a couple different papers. So there are two papers on the archive with the first group of co-authors. One is called Extremal Singularities and Positive Characteristic, which I'll mainly be focusing on. And I'll also mention we have another paper which is in transactions called cubic surfaces in characteristic 2. And I'll mention how those are an explicit example of some extremal singularities, and I'll get into what that is. And then I'll also mention some ongoing work with the second group of people, which is not on the archive yet, but hopefully will be maybe sometime this semester. And that's with the second group of people. So the first group of people, actually, this started in Banff. I joined the project after Banff, but it started in October 2019 with a question Karen had, and she was thinking about cubic surfaces characteristic 2 at the time, but we're actually going to start with a different motivating question. So I'm going to start with the following. I want to say, what is the most singular possible hypersurface? Maybe we fix a degree in characteristic P. All right, one answer to this question, we can think of a lot of different ways to measure singularities, but one of these ways is using something called the F-year threshold. So the F-year threshold, I'll tell you a bit about it, is something that in general, the smaller it gets, the more singular your hypersurfaces or your variety is. So one answer is those with minimal F-year threshold. Okay, so before I get into what we proved, let me tell you just a little bit about F-year threshold and motivate the fact that it's some sort of measure of singularities. So let me give you the definition so we can derive some basic facts about this invariant. So I'm just going to define it in the particular case we're working in. So we're only thinking about hypersurfaces. So variety is just cut out by one single polynomial equation. So let F, a polynomial ring, let's say K is characteristic 0, or sorry, K is not characteristic 0, it's characteristic P. And I want to define the F-year threshold at a particular point. So I'm going to just choose the point that 0, so the homogeneous maximal ideal. So I'm going to assume that I guess F is contained in the homogeneous maximal ideal. Then we're going to define the F-year threshold of F at this point. So at the homogeneous maximal ideal is going to be the supremum, well, n over p to the e, such that f to the n is not contained in m to the p to the e. And what do I mean by this? So m is the homogeneous maximal ideal, and this bracket p to the e just means I raise each of the generators to the p to the e. Another way you could write this is the inf over n over p to the e, such that f to the n is contained in m bracket p to the e. Okay, so the idea is when this ratio gets bigger and bigger, eventually all of these guys are contained in m to the p to the e. But there's some point at which there's a supremum over all of them where it's not contained, or if you want, that's the same as the infimum of all f to the n that are contained in m to the p to the e. So let's make some remarks. And I should say, I'll often drop this m. So throughout this talk, you can assume I'm thinking at the point the homogeneous maximal ideal, but I'll just from now on probably just write F pure threshold as a FPT. Okay, so let's make some remarks. Okay, just from this definition, actually I want to set some notation. So say F is as above, so it's still a polynomial and n variables, but say F is degree D. Variables. Again, K is still characteristic P. Then, so first of all, we can just notice, I guess the number 1 is in this set. So if I take the inf over this set, right, if I just take capital N equals 1 and E equals 0, I always have F to the 1 is contained in the maximal ideal. So I have 1 is in the set, so the F pure threshold of F is bounded above by 1. Also, I have that 0 is in the top set, so the F pure threshold is bounded below by 0, and you can actually show that's strict. In fact, you can show it's not too bad. That n ranges, or F, sorry, the F pure threshold of F can range between 1 over D and n over D. So 1 over D is kind of an easy lower bound to give, and n over D is a not too difficult upper bound to give. And in general, we can think of this, so it's some invariant that ranges between 0 and 1. And I want to think of this as the smaller this thing is, the more singular my hypersurface is defined by F. Maybe I'll think of it that way. And to give evidence to this, okay, if I say, if F is smooth, and this is at the point 0, then F pure threshold is 1. Maybe one more remark, for any R, the F pure threshold of F to the R, and you can do this directly from the definition, is just the F pure threshold of F over R. Okay. For example, just using this last thing, I can notice that I look at the F pure threshold of X to the D. Well, X is smooth, right? So I should get F pure threshold 1. So I just get 1 over D, just applying this last property. So I can actually attain this lower bound here. But I want to show you, like, what our theorem will say is that this is kind of the only way to attain this lower bound. Is the only way we'll attain this lower bound is when we have something like this, which is not reduced. So maybe I should go back up and modify my question. I'm going to say, what is most singular possible? The ones I really care about are not the ones that are singular just because they're not reduced, but I want to say, what is most singular possible? Reduced hypersurface. So I'm going to give a bigger lower bound in the case when we are reduced. Maybe I'll do another example to convince you that this thing actually tells us something about singularities. So I hope that it can distinguish between some different singularities. So if I look at these two polynomials, these give things that are singular at the origin. But we hope that this one is less singular than the other one, right? This one in some sense should be more singular. And in fact, the F pure threshold tells us that it is. So here the F pure threshold of xy is 1. And here the F pure threshold of y squared minus x cubed. And this one actually kind of depends on it does depend on the characteristic. So this thing is kind of, in a sense, more singular in characteristic 2. And then it's also pretty singular in characteristic 3. And then we get 5, 6 when P is 1 mod 6. And 5, 6 minus 1 over 6P 1p is 5 mod 6. But in all cases, of course, this gives me something more singular than the case over here. All right, and for those of you who like characteristic 0, if you're familiar with something called the log canonical threshold, this is some sort of characteristic p analog of that as well. So that's a measure of singularities in characteristic 0. I'm not going to say too much about it, but there is a precise way in which by reduction mod p, these things are analogous in some way. In fact, the F-pure threshold in general, I guess I should just say, if I do a reduction mod b, the F-pure threshold is always less than or equal to whatever the log canonical threshold was. So it's a lower bound. But in general, we'll see that like things in characteristic p can be much more singular. So this lower bound that we'll get, we actually can't obtain in characteristic 0. It just doesn't happen. And in characteristic p, we get these really singular things. Okay, I think I'm ready to state our first result. So again, this is the first group of co-authors. So lots of people. So what do we prove? We want to find some lower bound on this F-pure threshold. And again, we have to do it only in the reduced case. So if F is a polynomial in n variables, and actually we stick to just the case of homogeneous polynomials. So let's say K characteristic P, F homogeneous, and reduced of degree d, then in fact, the F-pure threshold of F is bounded below by 1 over d minus 1. So in the case that F is reduced, I get a lower bound that's bigger than 1 over d. It's just 1 over d minus 1. So the things that attain this lower bound, if there are any, should be sort of the most singular, at least with respect to F-pure threshold. And in fact, we can tell you exactly which polynomials attain this lower bound. So in addition, F-pure threshold of F is equal to 1 over d minus 1, if and only if F, let's say, the degree is p to the e plus 1 for some e, where p is the characteristic, and F is contained in the maximal ideal to the p to the e. Again, this is just x1 of the p to the e up through xn of the p to the e. Okay, so let me translate that a little bit. This means if and only if F has the following form. So it's got to have each of these generators. And then since it's a degree p to the e plus 1, all you can have left over is a linear term. Right, so this looks like xn to the p to the e times n, such that each li is linear in our variables. Great. I'm going to call this format star. And I'm going to say, I'm going to name these. I'm going to call F a Frobenius form whenever it has this special format. So these are all of the homogeneous polynomials that attain this minimal F-pure threshold in characteristic P. So definition, we'll say F is a Frobenius form. The name coming from the fact that I guess it's contained in this Frobenius power of the maximal ideal. Sometimes people call it that. If F has form star. And I might use the word extremal singularity or extremal hypersurface. And what I mean is just any polynomial which attains this minimal F-pure threshold. So all of these Frobenius forms. And maybe I'll refer to the projective hypersurface related to this. We'll say F, or maybe V of F, is an extremal singularity. Or I might alternately say extremal hypersurface. If the F-pure threshold f is equal to 1 over d minus 1. But our theorem says it's exactly these guys.
Janet. Thomas is curious to know whether this is in the preprint or the transactions paper.
This is in the preprint, so it's on the archive. Yeah, the transactions paper, actually, let's do an example right now. So for example, an example of a Frobenius form, I should say a star, is f equals x cubed plus y cubed plus c cubed plus w cubed in characteristic 2. So in fact, and actually there's a few others, it turns out that if I look at cubic surfaces in characteristic 2, so right, 3 is equal to 2 plus 1, 2 to the 1 plus 1. So this is something of this form. I could say, or any, it turns out that all of the cubic surfaces which have minimal F-pure threshold are actually just all of the cubic surfaces that are not F-pure. So any cubic surface. So we were looking originally at just degree 3 equations in 4 variables in characteristic 2. And we wanted to know which ones were not F-pure, which is not F-pure. And you can kind of convince yourself quickly using Fetter's criteria that in this particular case, just for the degree equals 3, this condition is the same thing as being F-pure, but in general, that's not true. So or any cubic surface was not F-pure is also a form star. So if you look at the paper and transactions, that will tell you a lot about cubic surfaces, which are not F-pure. And so that is a special example of a Frobenius form or an extremal singularity. And I'll say a bit more about that as well later. But good question. All right, so this form star is really powerful. So it has a lot of these Frobenius forms will say they have some really beautiful geometry. They also have some really beautiful algebra. So maybe a key observation. If F is a Frobenius form, we can make the following matrix factorization. So I can write F like this, where A is just some n by n matrix with coefficients in K. So if I look above, A is just the rows of A are just the coefficients in each of these linear forms, right? So this might remind you of like how we can factor quadratic forms, for example. In general, if I take away these p to the e's on this side, I can write a quadratic form as a factorization like this. And usually to make a unique choice of a matrix, I have to choose something like a symmetric matrix for quadratic forms. In this case, of course, A is actually unique, right? To get this exact polynomial, A is unique. Once I've made the choice on which side to put the p to the e's, for example. And this is where we're going to get a lot of power of the algebra of these Frobenius forms, is they have this like very beautiful matrix factorization. Further, if I consider a change of coordinates, so I want to study these things under linear changes of coordinates. Maybe I'll write it as a matrix. So let's say I send each of the variables to some matrix G. Again, this is just like an n by n matrix with coefficients in K times the variables. So I send x1 to g11 times x1 plus g12 times x2, etc. Then we can chase through just what happens to this form here. Let's call this change of coordinates phi. Then phi of f is equal to what happens is I get the transpose of G, and then I raise it to the p to d. This means all the coordinates raised to p to d, and then times A times G, and then again times this guy. In particular, I stay a Frobenius form, right? And that actually should have been clear before. F pure threshold is something that's invariant under linear change of coordinates. So if I had minimal F pure threshold to start, then I also should have it after I do some linear change of coordinates. And so I should still be of the form that I said are the only things that have minimal F pure threshold. But yeah, we can track through when I take a linear change of coordinates and I apply it to some Frobenius form. What I've done is I've just taken this matrix A and replaced it with a new matrix. So I can really understand what happens to these things under linear change of coordinates by just understanding this action on matrices. It's really cool. Okay, so we'll make the following definition because it will be useful. A Frobenius form is rank R if the associated matrix A has rank R. And notice that this is something that is invariant under change of coordinates, right? If this was really a change of coordinates map, it better be full rank. And so G transpose to the P to the AG will also be a rank R matrix. So this thing is invariant under change of coordinates. Okay, I think I'm ready to state our second result. So the first thing, I mean, our goal now, the first thing we do is we show exactly which ones obtain this minimal F pure threshold. And then what we're going to do is we're going to classify them fully with respect to linear change of coordinates and actually tell you exactly what they are after linear change of coordinates. So again, this is the first group. Oops, sorry, let me reshare my screen. Right. So this is working towards proving exactly what all of these are up to change of coordinates. And the first thing is to show that there's actually only one in full rank. So there's actually only one full rank one. This actually was known by Beauville in 1990. But the method, and actually I should say this is only for n bigger than 4. We'll show it for all n, and the methods we use are actually a lot simpler. So we really only use some really clever polynomial algebra and Hilbert-Nussbaum, and that's how we get this theorem. So we use kind of really elementary methods, and we don't use any heavy machinery at all. So if F is a Frobenius form, of rank n, I should say in n variables, of rank n, then after some change of coordinates, we may as well assume that F is just this one, which I will call the Fermat. In other words, my matrix A, I can assume after change of coordinates, is just the identity matrix. So all of these are projectively equivalent to each other, and all the full rank ones. In fact, we're able to show, so there's only one for each that's full rank, but we'll be able to show that also there's only finitely many of other ranks as well. That's our next result. There are finitely many Frobenius forms in any, I guess I have to fix the number of variables, so any bounded degree and any bounded number of variables. More specifically, there is a projection of the partition numbers of n so the partitions of the number n with Frobenius forms which are non-degenerate. So by non-degenerate, I mean they won't be able to be written in a smaller number of variables, in n variables. And if I fix any degree. So the degrees always are of the form p to the e plus 1. There's exactly the same number, no matter what e I pick. And that number for n variables is the numbers of partitions of the number n. Degree d equals p to the e plus 1. Okay. I want to sketch the proof because I think it has a lot of really interesting elements to it. So I'll and I'll also show you kind of exactly how to get these partitions. So you'll see where these are coming from and how to write down all of them up to linear change of coordinates. And of course, this I didn't say, but it should be up to change of coordinates. Of course, there are infinitely many if I don't consider up to change of coordinates. Okay, so here's the step. So first, by induction, and also a lot of linear algebra, show that without loss of generality, meaning after some change of coordinates, we can assume the matrix A associated to a Frobenius form has at most one non-zero entry in every row and column. Okay, so this, oh, and actually we can assume, and it is a 1. That last bit is just by scaling, that's kind of the easier part. But yeah, this uses a lot of sort of delicate linear algebra, also sort of delicate combinatorics and an inductive argument, and it also uses theorem too. So it uses the rank n part. And actually, so we put a version of our paper on the archive, I think last September 2020. And this is all we had at that point. So this actually shows that there are finitely many, right? There's only finitely many matrices with at most 1, 1 in every row and column if I fix any size n. So this gave us finitely many, but we couldn't quite get the full classification. So we couldn't tell you, we knew that some of these actually gave the same Frobenius form up to change of coordinates, and we couldn't quite get it. And so eventually the key bit that we realized was associating a directed graph in a particular way. And that's sort of what made the full classification a lot easier. So maybe I'll say, I'm going to call a matrix A sparse if it has this property, if it has at most 1, 1 in at most one non-zero entry, which is a 1 in every row and column. And I'll kind of show you the difficulty of this. So we were kind of stuck here. However, we knew that, for example, we could also make some other assumptions about the matrix A. So we could assume that it sort of had an anti-diagonal format. So the ones kind of appear going in this order. But that also wasn't enough. We knew, for example, the following two matrices give linearly equivalent Frobenius forms. Oops. So these two rank 3 Frobenius forms and 5 variables are the same. Maybe I'll write them out. It's not too hard to see that they're the same. And the other one is the same except for the last term. So x1 to the 3e x5 plus and if you're really bored and need something to do, maybe convince yourself that there's a change of coordinates that takes one to the other, and it's not so hard. You just swap a few variables around. So we could make some other reductions on A, and on our first version of the paper we did, but for whatever reason we couldn't. Both of these sort of were fit into all the reductions that we could figure out how to make, and we couldn't quite get a unique representative for every Frobenius form. Okay, so the breakthrough was realizing the following definition, which sort of captures all the relevant combinatorics that's going on here. So, and all the algebra that's going on, I guess. Given a Frobenius form F I'm going to call it sparse form, meaning its matrix is sparse. Associate to F a directed graph. I'll call it gamma F on n vertices. The vertices just corresponding to the n variables. I'll draw an edge from xi to xj whenever xi to the p to the e xj is a term of F. Okay, so I'll do an example really quickly. Maybe I'll call this example 1 and example 2. So in my first case, I would associate x1 to x5, x2 to x4, and then x3 to x2. And in the second one, I would associate x1, x5, x2 to x4, and x3 to x1. And hopefully now it's easier to see that these things are exactly the same. Of course, if they give the same directed graph, there's some relabeling that will just make them exactly the same. Maybe I'll do another example to show you what else can occur. So in this case, I would have a loop on x1. I'd have x2 to x3, and then I have x4 goes to x5, goes to x6, and then it goes back to x4. So maybe we'll make the following observation. What can happen in this graph? This can have, well, it can have loops, right? If I just have a term like I to the p to the e plus 1, so it can have a loop. It can have what I'll call a directed chain, so just something that looks like this or that looks like this. Or it can have what I'd call a directed cycle, so something that comes back to itself. But I know that I started with a matrix that had at most one non-zero entry in every row and column. A non-zero entry in a row is like an arrow going out of a vertex, and a non-zero entry in a column is like an entry coming into a vertex. So every vertex has at most one arrow leaving it and at most one arrow going into it. So these are actually all the things we can have. And for example, I can't have a chain that points to itself at some point, because so when I say directed chain, I really mean all the arrows are going the same way, right? Because then I would have either two arrows facing each other or two arrows pointing away from each other. And also cycles, we can't have anything coming off of the cycle because everything in a cycle has an arrow going into it and an arrow going out of it. So this is all the things you can have just by the assumptions on A. Okay. Oh, maybe I should make a side note. This is kind of a backwards definition, but A is the directed adjacency matrix of this graph.
I do have a question.
Yeah.
The directed adjacency basically you don't have, for example, two things coming out of X4 because really there should be like a change of variables to prevent that from happening. Is that what's going on here?
Yeah, so what happens is our first step. Yeah, exactly. So if I were to draw, so I'm only going to define the directed graph for things that already are in this like sparse form. So the first step, our like first induction, shows that like everything is equivalent to a graph that only has edges like one going in and one going out at most. In other words, everything is projectively equivalent to a matrix with at most 1, 1 in every row and column.
Okay,
so that's the first
where the
step.
Change of variables comes in, I guess.
Yeah, that's where the change of variables come in. Yeah, so this is this is a lot of work. I shouldn't underplay this at all. There's a lot of sort of careful induction there, and that was the version we had in our first version of the paper. I don't want to go through that because I think it's less pleasant to go through in a talk, but I think this is kind of a fun way to see kind of the end of it. But yeah, definitely the first part of this also used a lot of really careful arguments and a lot of induction. So there's a lot of work that goes into the induction. But yeah, definitely reducing the fact, showing that like every Frobenius form is like something kind of very sparse is like a big theorem.
Yeah, no, this is a really cool thing about it. Is this directed graph too. It's really cool. Thank you.
Yeah, no problem. So the next step. Okay, so first what we did is we showed everything was equivalent to some very sparse matrix. Then I associated a directed graph. And then the last thing I want to do is I want to get rid of the cycles. So note, if F has a cycle, sorry, I should say if gamma F has, I'm going to say an L cycle to mean the number of vertices. So I'd call this one a 3 cycle. Oops. Then it's of this form. So I might as well just label that cycle x1 through xl. So it looks like x1 to the p to the e, x2 plus x2 to the p to the e, x3, xl minus 1 to the p to the e, xl, and then it goes back to x1. Plus some other form. It's also going to be a Frobenius form, and it's in only the other variables, right? Because cycles already have, they already have every vertex has an arrow going in and an arrow going out. So xl plus 1 up through xn. Okay, but now we know that this is a full rank Frobenius form in L variables. When you have a Frobenius form that's sparse like this, the rank is just the number of terms, or if you want, it's the number of edges, or it's the number of ones in your matrix, and there's L ones here, right? There's one starting with everything from 1 to L. So by theorem 2, there is a change of coordinates on just the variables x1 through xl, so that F is equivalent to, I can just replace these all with loops. And then I still have this other thing that's untouched because I just did a change of variables on the first L coordinates. In other words, I'm saying that I can replace all of the cycles with loops. So without loss of generality, F is equivalent to some G, so that gamma G has only loops and chains. Because I can repeat this process as much as I want. Okay, and now finally I can associate a directed graph. Now, or not, sorry, not a directed graph, a partition. Now associate a partition to G by the number of non-zero, the number of vertices in each component. Of this new directed graph, the one with only loops and cycles. So maybe I'll run through our examples. 1 and 2. I'm going to call this, so there's 2 elements, there's 2 vertices in one piece and 3 in the other. So these are both the partition 2 + 3 = 5. And then this one, I would replace this part with 3 loops. And I get, I guess, 1 + 1 + 1 + 1 + 2. So this is examples 1 and 2. The picture was like this and this. And then example 3, we reduced it to this guy. And like that. And this is a partition of 6. The other one was in 6 variables. Great. So now, I guess the final step is to notice. So already we have that, like, clearly if I have 2 different Frobenius forms, if F1 and F2, let's say, have the same partition, then they're projectively equivalent to something which has the same directed graph, and then just by some relabeling, they're actually projectively equivalent to each other, right? Then F1 is projectively equivalent to F2. There's some linear change of coordinates that takes F1 to F2. We also show that the only way to have the same partition is for them to be linearly equivalent, or to be equivalent after some change of coordinates. So we also show that if F1 is equivalent to F2, then F1 and F2 have the same partition. And this uses some algebra. But it also uses this directed graph. So we look at particular vertices in the directed graph, and we show sort of that they have to be taken from one to the other. And anyway, we show that these things have to have started with the same partition to start. So, but I'm not going to go through that proof fully. Okay, maybe I'll just say, so that's the full classification. Maybe I'll say a few things about the geometry of these things. I've talked a lot about their algebra and I've given their classification, but I want to say kind of why they're special geometrically, other than having sort of this minimal after threshold. So geometry. So maybe I should make an overall comment. So when we're studying the F-pure threshold, you can think of it that as studying the singularity at, so I want to study projective hypersurfaces defined by these things. But what F-pure threshold is measuring is it's looking at the affine cone over this projective hypersurface, and it's looking at the singularity of that cone point of the homogeneous maximal ideal, so of the origin. So the projective hypersurface defined by this polynomial, it could be smooth. The affine cone over it is not. It's going to have a singularity at the origin. But we're going to study the geometry of these projective hypersurfaces. So hypersurfaces defined by these Frobenius forms. In fact, maybe I should just say the only smooth one, there's actually exactly one that gives in each number of variables that gives a smooth projective hypersurface, and it's the one that's full rank, so it's the Fermat. All the other ones give singular projective hypersurfaces. Of course, the affine cones over them are also singular. But I'll make the following remark. So suppose I look at some hypersurface defined by a Frobenius form. Oops. And let's say I have two lines on this hypersurface that intersect. So I guess there's two cases. So if these things, the plane they span is not actually contained in X, so maybe I'll say let lambda be the plane they span. So if this wasn't just itself an X, then if I look at its intersection with X, so I take the plane spanned by these two intersecting lines and I intersect that whole plane with X, what I get is either a p to the e fold line intersecting another line. So one of my LIs actually had like a bunch of lines along with it. Like this. Or I get what we call a perfect star. So what I mean by that is p to the e plus 1 lines intersecting at a point. And also after some linear change of coordinates, I can assume that the slopes of these lines vary through the p to the e plus first roots of unity. In other words, these things are all equally spaced. So that's what we mean by perfect. But that's p to the e plus 1 lines intersecting at a point. Okay, so maybe I'll say some examples. Or maybe I'll say a consequence first. So X has no configuration of lines that give a triangle. So X has no. So generally, if I find like 3 lines on X in the same plane, I would expect that they probably intersect in this configuration, right? And what we're saying is that this never happens. Actually, the only thing that happens is if there's 2 intersecting there, then actually the whole degree is intersecting there. So all p to the e plus 1 are intersecting at that particular point. So our first paper was a lot about cubic surfaces, so I'll say a few words about that. So we know smooth cubic surfaces have 27 lines in general. And there's one smooth cubic surface that's given by a Frobenius form. So it's only the Fermat, the full rank one. So x cubed plus y cubed plus z cubed plus w cubed. And the only Frobenius form that's cubic is the one in characteristic 2. So, but in characteristic 2, the smooth cubic surface has no triangles. In other words, every single intersection point is what's called, usually in cubic surface land, they call a meeting of 3 lines an Eckhart point. So every intersection point on this cubic surface is actually an Eckhart point. And of course, there's also some non-smooth Frobenius forms which give cubic surfaces. Those also have no triangles as well. So all the intersection points on them are also Eckhart points. In fact, this is the only cubic surface in any characteristic. I should say smooth. This is the only smooth cubic surface in any characteristic with no triangles. So this theorem is a theorem in our transactions paper if you want to look at that one. Okay, I'm just about out of time. I wanted to sort of advertise, so everything I've mentioned so far is work with the previous authors, and I want to just advertise really quickly work that you should look out for. So our ongoing work. Is we're studying more of the geometry of extremal hypersurfaces, but we're going to focus on the surface case, so the case in 4 variables, but not just cubic surfaces. We're going to look in any degree. So 4 variables. And maybe I'll just, since I'm basically out of time, maybe I'll just mention some of the things we study. So we especially focus on the smooth case, although we also study things about all of the cases. Again, there's only one smooth case in any fixed degree. And what do we know about these things? So for example, it has tons of lines on it. We can count the lines on it. It's got tons of stars on it. The automorphism group on this thing is really large. For example, it acts transitively not just on lines themselves, but actually on triples of skew lines that are on this surface. If you have any 3 skew lines, you can determine uniquely a quadratic. That quadratic, if I intersect it back with my surface, actually gives just a configuration of lines and always gives kind of the same type of configuration of lines. And the automorphism group also acts transitively on that thing. There's also a really interesting, so if you've studied smooth cubic surfaces, there's something called a double 6, which is a configuration of 12 lines with a special configuration that lies on every smooth cubic surface. And actually these extremal surfaces have sort of an analog of a double 6. So in some sense, we show that they're sort of geometrically, in some sense, like a generalization of cubic surfaces, which is really neat. So it's kind of like algebraically, I think of these as some sort of generalization of quadratic forms with this matrix factorization, but geometrically, they have a lot of properties in common with cubic surfaces. Okay, and I'm out of time, so I'll stop there.
Let's thank Janet Schill. Any questions?
Yeah, I have one more thing. Right, so you have to forgive my first question. It's flooding back to me the transactions paper. It's been a while since I've read that, but I remember that being a lot of linear algebra, arguably very appropriate to even work through like with an undergrad student with. It's really beautiful paper. Very nice. Would you say the same about the second one, that the techniques of the classification would still probably be appropriate for an undergrad student to try to work through? I'm asking because it looks like I might be acquiring an undergrad student or 2 for some directed readings.
Yeah, so sort of. So I would say that we don't really use any high technology. So
Okay.
yes, hypothetically, I would say that the arguments in the second paper get a bit more delicate. So I think maybe they're a bit, I don't know. If you have a very mature undergraduate student, then I think they can probably work through it because we don't really use any heavy machinery at all.
Okay.
So yeah, if they're willing to sort of do some delicate arguments, then it might be appropriate. But other than, of course, like definitions of F-pure threshold and stuff like that, they'll need a little bit more background on F singularities. But a lot of the arguments we use, yeah, really don't use any really heavy machinery.
Okay, thank you.
So I have a question.
Yeah.
Yeah, so I see in the definition of the F-pure threshold, you define to be the securum of N over PE, where Fn is not in the Frobenius power, right? So my question is there an analog definition when we replace the Frobenius power by the ordinary power?
Off the top of my head, I'm not sure if that matches up with anything. So there are other notions. Yeah, let me scroll up to this. Yeah, I think if you take this exact definition and say ordinary power, I'm not sure that that does anything. It's almost like taking a supremum over like a differential power of f or something like that. So anyway, maybe I won't say. I think if you remove this bracket p to the e. Actually, no, won't we just get the multiplicity? Sorry, yeah, actually, if you just do this, I think you get the multiplicity. If you, yeah, if you work through this, I think you'll just get the multiplicity of f. Or there's a very similar definition that, or 1 over the multiplicity. Yeah, I think you'll get the 1 over the multiplicity. So question, or maybe check. The supremum of n over p to the e. I guess if you take the supremum of all, maybe not quite. So if you do a supremum of all n over just anything like n over t, such that f to the n is contained in m to the t, where you do ordinary powers, this is, I think, by definition, the multiplicity of f. So for a homogeneous polynomial, this should just spit back. This should just spit back exactly the degree.
I see. Thank you.
Maybe I have to say something like, if I assume these are in Q. Actually, it shouldn't matter. Yeah, so this will give you the multiplicity. Yeah, so actually, that's sort of the most naive, or sorry, not multiplicity. It should give you 1 over the multiplicity. One naive measure of singularity is just taking the multiplicity, right? Like in general, I think of things of higher multiplicity as more singular. But of course, multiplicity doesn't distinguish between a lot of singularities. So for example, these two things are both multiplicity 2. Or sorry, yeah, these are two things are both multiplicity 2. But of course, one is much more singular than the other. But yeah, so I think you should get, and this is roughly a way to think about a pure threshold, is it's kind of like a refinement of 1 over the multiplicity. Yeah, double check this for me, but I think this is right, that it's, you just spit back the multiplicity.
Okay, okay.
Another question?
All right, let's thank Janet again.
Yeah, great talk.